Hello, everyone. Good morning. Thank you so much for this opportunity from Equal Experts. And thank you all for being here today to attend this session. Today, we are going to talk about building a scalable state of art authorization platform with graph database. Just a quick introduction about ourselves. I'm Rajeswari Krishnakumar. I have about 13 plus years of experience. Currently, I'm an engineering manager with Freshworks. I lead the authentication and the authorization platform for all the Freshworks suite of products. Over to you.
Yeah, hello everyone. A very good morning. Yeah, I'm Jayabarathi from Freshworks. I have been a staff engineer in Freshworks and I'm also part of the IAM platform for Freshworks that is taking care of authentication, authorization, and all the security features for all the Freshworks suite of products. I have nearly 10 years of experience and I am skilled in building scalable distributed systems. I like to bring clarity to places where there is less clarity, and I like to drive the architectural direction for long-term customer impacts. Yeah.
So just a little bit of history here. We have been building this authorization platform for Freshworks. Since the ideation phase, it's been around like 2-ish years that we have been, working on this. And we are here today to share our learnings along this 2-year journey that we have had. So this is the brief agenda. So we talk about authentication and authorization and how it works at scale, the different authorization models that are available today. We'll pick up a real world SaaS use case and we'll go a bit deeper into it. Uh, we'll also discuss about the common approaches that you can use to solve this real world use case. We'll dive deep into graph databases and the related tech around it. We'll also briefly touch upon our authorization platform architecture, and we'll close with some key learnings that we'll share today to take away for all of you. Okay, let's start with like basics. Uh, Authentication and authorization. So I think like most of you will kind of have an idea about it. Authentication is about who you are, and authorization is can you do something that you are you authorized to do something? Are you allowed to do something? That is the authorization question. Let's say, for example, like you go into your office building, okay? When you go into your office building, you'll swipe your badge at the entrance, right? That will verify your identity. It'll tell you whether you can enter this building or not, whether your identity is verified, that you work for this particular company inside this building, and it will let you in. That is authentication, correct? And let's say your office is on the 10th floor of that building, okay? So you go into the lift and you swipe your badge again. Then it will only let you select the 10th floor in the lift, right? It will not let you select the other floors. That is authorization. Got it? So these two are very critical for any system, given how much traction security is getting these days. Today we are going to focus mostly on authorization. Authorization is a first-class system concern. So every click that you do inside whatever application you use is an authorization concern, correct? Because if you do something unauthorized, it will result in a big security violation. So, what is the impact of having a bad authorization layer? If it is slow, your entire product feels slow. Let's say like all your authorization checks take more than 1 second. So every operation that you do in the system will go through your authorization layer and everything will take a latency of more than 1 second. So your entire product feels slow. If the authorization layer is incorrect, it will result in a huge security risk. There'll be a huge security violation. There'll be unauthorized access, and you lose all your data. If the authorization layer is inconsistent, it will result in broken user experience. And if it is hard to evolve, your entire product velocity slows. Say if you just have to add one or two policies to your authorization layer, but it takes months and months for you to implement that, your entire product velocity slows. So it is very, very important to have a very performant and an authorization layer that is very easy to evolve. Let's also see why authorization breaks at scale. Okay. So let's say this is like a typical service level authorization. There is a user, he makes some requests, it will go through your API gateway. You have, let's say, like three services, right? All your three services have their own authorization implemented independently inside each of these services. Do you think this will scale? Okay. And your modern SaaS, what it actually needs from your authorization layer. It requires multi-tenancy. It requires dynamic roles to be configured. It might or might not have nested groups. It will definitely have resource hierarchies. And there again might be a need for custom permissions. So your modern SaaS applications mostly have at least 4 or 5 here. And it must have less than 50 milliseconds latency. It should be scalable for millions and millions of checks per day. It should have 100% correctness, and it should operate under very strict isolation, right? So this is the requirements. This is the scale that we are looking at. And let's see how we have built it for the same scale. Let's also see the different authorization models landscape that are today available. First one, most common one is the RBAC, role-based access control. So let's say you have like three users and all of them have different roles associated with them. Okay. So your role-based access control, what it does is it will simply say a user with this particular role can do these set of actions, are allowed to do these set of actions, right? So here Alice is an admin, and under admin privileges, she can create articles, view articles, edit and delete articles, and also manage users. Similarly, Bob is an editor. He can only create, view, and edit articles. Whereas Charlie is a viewer, he only has viewer privileges, which means he can only view the articles. So now the modeling is very simple. There's a user, you assign one role to him, and then all the set of privileges that are associated with that role will start applying for that user, right? So this is a very common use case. This is good for straightforward use cases. But under like complex SaaS, it might not be very straightforward to define roles for users and just uh, go with it for scale. Some of the SaaS products will have like nested groups, we said, right? And some of them will have like different definitions of how the resources are. So under these things, there'll be a role explosion. So for each and every specific set of privileges you want, you should be like defining separate individual privileges and assign roles accordingly, which might result in a role explosion. The next common model is RBAC, relationship based access control. So here what we do is we have different users. We will associate them to a particular department here. So you say like Alice is a member of tech department. Charlie is also a member of tech department. But Bob is a member of HR department. And then we can define rules saying whoever is a member of a tech department can edit the tech documents. Whoever is a member of HR department can edit the payroll documents. This is relationship based. You try to form a relationship between your entities and then define your access policies based on that. The next one is attribute based access control. So here what you do is you pick some attributes for your users and then define your access policy based on that. So here you can say like Alice has role admin and her department is tech, but Bob's role is editor and his department is HR. Now I want to define a policy who's allowed to edit the tech document. So in this case, what your auth engine will do is it will pick some parameters here and then define the policy. So if the user role is admin, then you can allow. If the user department is tech, then allow. So in this case, Alice will be allowed to edit the tech department document, but Bob will not be allowed to edit because neither the user role parameter is satisfied or the user department parameter is satisfied. So he'll not be able to edit. This seems like a better approach compared to the previous two ones, but again, it's very difficult to define the entire set of rules, and it will be very difficult to maintain at a huge scale. If somebody gets authorization for something, it will be difficult to go back and see why that person got access. That is also one of the problems that we observe. So the next one is the policy-based access control. So generally, your org will have certain policies. So let's take, for example, this policy. The on-call, the NOC engineers can restart production services only during approved maintenance windows. This is a policy that is defined by the organization. What PBAC does is it translates the same policy into a condition that is run under a policy engine. So here, Alice and Bob are tech engineers, but Alice is a NOC engineer and Bob is a general software engineer. And then you have your other parameters like what services are there, what is the ticket status and everything. So based on all these, we'll build a policy engine. And here you can define the condition saying if just translating what the policy is to simple if else condition. If the user role is a NOC engineer and service environment is production, and the current time is within the maintenance window, and your ticket status should also be approved. Only then allow service restart. So here it's not just taking the attributes from the entities, but it is also bringing in some kind of business logic to it. This current time is within the maintenance window. That is the business logic that is coming in here. So this is again like one of the very effective authorization landscape. But again, there will be some issues where like it will be difficult to trace back to how this person got access and everything. So there are like advantages and disadvantages in all of that. That's what I was trying to say. So let's get into the real world SaaS use case. So you all know like Freshworks is a SaaS product, SaaS company, and it has like multiple SaaS products. Some of the famous ones are like Fresh Service, Fresh Desk, Fresh Sales, etc. So we'll probably like look at what kind of authorization is needed for these products. So let's say there is a big tenant, okay, and this is how the users are there within this tenant. So you have Alice, Bob, Charlie, and everyone, and all of them have role associations. So all of them have roles assigned. Alice and Bob are HR agents. Charlie and Dave are billing agents. Eve is a support lead. France and Grace are support agents. And Hayden is an operations manager. So he takes care of everything, right? Support lead takes care of the department tech support, and the department hardware and software are within the department tech support. HR agent applies to the HR department, billing agent applies to billing department. And Frank is a support agent for the hardware department, whereas Grace is a support agent for the software department. But your operations manager can belongs to like all the departments because he is the operations manager. We have just condensed our entire use case into a very simplified use case for sake of understanding. Okay. Now let's say there is a ticket 123, which is a payroll issue ticket, and this ticket belongs to the HR department. Okay. And then we have 456, which is a refund request, and it belongs to the billing department. 789 is an API error. It belongs to the software department. So let's now ask some questions through this relationship graph to see if you know this particular user can access this resource or not. Can Bob access 123? Yes, because 123 is a HR department issue, and Bob has role HR agent, which applies to HR department, so he can access it. Can Frank access 456? Answer is there. Frank cannot access 456. 456 belongs to the billing department, but Frank is the tech support guy, so he cannot access it. Can Eve access 789? 789 is a software department request, and Eve is a support lead, so she can access both hardware and software tickets. So Eve can access this. Can Hayden access 456? Yes, because Hayden is the operations manager. So he should access all the tickets. So this is how the authorization graphs are kind of built at a very high level. And these access check questions are also answered. So we'll probably like get into a little deeper on these concepts, right? So when you say authorization, there are two major things there. One is the ACL management, and the other one is the ACL validation. What is ACL management? ACL management defines how the users are defined, how are the roles configured, how are the users related to one particular resource. So if you see in this case, right, all of these mappings and how, for example, there's another user who's joining the company, how are these mappings going to be configured for him? What is the role that needs to be configured against him? And how it is there in the entire graph. How will the graph change if there is a change in the user or the role or a resource? All of that comes under ACL management. Basically, how your graph will change when your users or roles or the resources change. That is ACL management. What is ACL validation? These are the access query patterns. When building your system, what kind of checks do you want to make in your system? What is your use case? Do you always want to ask, can this user access this? Or do you want to do something else with the graph? So all the access query patterns come under your ACL validations. And it's also very important to see which one's the most frequently used access pattern so that you optimize your architecture for that. So your access query patterns, one of the type of query patterns is your permission level queries. So you start from your permissions and you ask questions based on that. For example, check if the user has the given permissions on the resource. That's it, which means like check if the user Alice has report view permissions in the tech support department. So here your query is based on the permission. You are checking if this user has this particular permission on this resource. You can also list all the permissions assigned to a user. List all the permissions for user Bob across all departments. Simple question. Return the permission list for a user on a single resource. List all the permissions for user Charlie in the billing department. And return all the permissions list for a role. You can say like, give me all the permissions that an HR agent can do. The next one is resource level queries. List all the, sorry, return the list of all resources for specific type in which the user has a given permission. So here the center of your query will be the resource. List all the departments in which the user Frank has report view permission. So these are the different type of access queries that you might come across while designing an authorization. Over to you.
Okay. So I'll dive a little deep into a few of the architectural decisions in building a platform level authorization solution. So to start with, uh, for authorization, consistency is the foremost important factor, because if a particular access query returns a stale information, it can lead to access leak that can leak a secure data to someone unintended. So when we speak about consistency, the first thing that comes to our minds will be relational databases. So being in software industry for a longer duration and building many applications, I think most of us will be very proficient in relational database, and we tend to choose relational database as a default whenever a particular use case comes. So if we try to evaluate a relational database for building an authorization solution, we could see there are a lot of concerns and bottlenecks. So as Rajeswari was going through the uh, entities and the relationships, right? So we have to correlate multiple relationships, and we'll have to do multiple joins in order to infer the data that we require. So it will result in very easily up to 5 to 7 table joins, where we'll have separate tables for users, user groups, where you will have a group of users, and you might be assigning the roles for a user group or for a user directly. And the groups can also have subgroups nested within. So likewise, depending on the complexity of the product, the number of tables that we'll have to join will keep growing. And MySQL will have our relational database will have complexity, and it will have computational overhead in doing these many joins to return a response. So the next foremost factor important for authorization is how speed it is. So when we do these many joins, obviously it's going to take more time. Authorization is a important and must required part for every function that we are going to deliver. So it shouldn't impact the overall functionality's performance. Hence, it has to be ultra fast, and the latency expectation will be in milliseconds. So these are the bottlenecks that we will see if we are going with a traditional approach. So it will lead to slower authorization checks, leading to slow down every functionality, and that might result in customer frustrations as well. So let's see how Google solved it. This is not a new problem that we are solving. Every system, every company who's dealing with the secure data requires authorization. And if we take Google, we have use cases from Google Drive, YouTube's, and all the other Google products. So Google has solved it using a relationship-based access control model as the base, and they have developed a globally distributed authorization. I would say globally distributed consistent database in order to solve this use case. And they have published their solution as a white paper, and that is called Zanzibar. So Zanzibar is a white paper that covers Google's authorization solution. So I'll touch upon what are the core concepts that Zanzibar states, and where all it will be applicable in a SaaS use case. So Zanzibar uses a tuple-based model. So how we define the data? That is the first question when we are trying to solve a problem. So whether we take a relational database and put it into tables, or whether we take a key value store or a non-relational database and we use it to store the database. So thinking on those lines, Zanzibar came up with a structure which is called a tuple, and they used this to define every entity that will be required to take the authorization decision. They also had the support to iterate through any number of hierarchies and recursive relationships using this tuple structure itself. And they ensure to provide a strong consistency using the database, which is called Spanner. So, this is a globally distributed relational database, actually. And how the consistency is achieved in this is they use globally synchronized clocks to ensure that the data is distributed across multiple systems and is in sync to the precision of a particular time. And also they use snapshot based retrieval. So at a particular point in time, any number of queries that is being made will be retrieved from a particular snapshot, and that snapshot will have the latest data. So there are while Google has established the base solution for authorization, there are multiple providers who have built on top of Zanzibar's concept, and they have built authorization solutions that are ready for integration. So if you are a fast growing company and you don't want to spend time on authorization and you wanted to integrate with some third party vendor, based on this Zanzibar, we have few providers, which is SpiceDB, Permify, Keto, and Warrant. Among these, SpiceDB is the one like who has implemented around 75 to 80% of what Google Zanzibar suggests. So we also started exploring SpiceDB when we initially wanted to build a scalable authorization solution. Yeah. So as I was telling, the tuple structured storage is the base for Zanzibar concept. So if we see here, the object, the object relation, and the subject. So these are the three major entities that defines how we are taking the decision. So subject here will be the user or user group where we have a list of users. So it can be anything who's going to perform the action. So that we call as subject. And object will be the resource that the subject is trying to access. And these two will be related using the relationships. So to take an example, let's say a document 123 is okay, a document is there, and how do we decide whether this particular document has whether a user has access to this particular document or not? So Zanzibar uses a declarative permission modeling. So if we have to define a permission, it will be a combination of relationships. So based on the relationships, you can aggregate them by using or conditions or and conditions and define who can access the document. So if you see here, view document is equal to viewer plus editor, which means anybody who's associated with the document via the viewer relationship or the editor relationship will be able to view the document. And each of these relationships will also be declarative. So it will not be like you can associate anybody with that relationship. So it defines a schema, and in that schema, we specify who can be allowed to add into that relationship. So here we have said for a editor relationship, any user who's part of the admin group will be allowed to have the editor relationship. And now, if we check if any of the admin user has access to the view document, then uh, via the permission definition where we have the editor, that particular user will get the view document access. So this is how uh, permission is verified in Zanzibar, and this is how it is being modeled using a tuple-based data store, tuple-based storage. So while that is the base from which SpiceDB was built, and we have evaluated SpiceDB for our use cases by doing some performance tests and load test executions. So we were able to figure out few advantages and the limitations where we couldn't apply or use SpiceDB directly for our complex use case. So the advantages are like um, there is an aggressive caching of subgraphs as part of the SpiceDB solution. I missed to cover on the part where it is a graph. Let me just cover that. So when we say permission view document is equal to viewer plus editor, right? So when we are trying to check for the view document permission, this will be divided into two subqueries, whether the user has viewer relationship on the document or whether the user has editor relationship on the document. So these two queries will be executed in parallel, and both of these will be separately cached. So tomorrow when we are trying to check for another user or for the same user, right? So whether the user has view permission, so the subquery, which was evaluated already while trying to check for the editor permission, will be reduced. So here it is a very simple example about just a view and edit permission. But in a real world use case, there will be multiple such relationship evaluations happening for a single user to define whether he has access. And for the same user, when you're doing any other operation as well, all these subqueries will be repetitively required, and hence the caching of these subqueries improves the efficiency of the evaluation pattern. So that is the core concept that leads to less than 15 milliseconds of latency. And so, one other observation is that it was a perfect fit for traditional access control patterns. So, when I say traditional, the most frequently asked question in an authorization system is, can this user access this particular resource? Can this user perform this particular operation? So, it is always a check of a particular permission for a particular user on a resource. So SpiceDB is optimally built in order to answer this particular query pattern, and as well as associated query patterns like retrieve all the resources where the user has access to. But the complexity that we had as a platform was we had to retrieve all the permissions that the user has and across all the resources within a particular system. The reason being, us being a platform solution, we had to support multiple products, and we will have to return all the data at once so that it will be used by them in a collective way to take multiple decisions. So, in order to solutionize this complex query pattern, we were struggling with the improved latency, the increased latency with the SpiceDB solution. So, based on our performance tests, we were able to see it was taking around seconds to respond for such a complex query, which was not agreeable. And also, one other important factor is authorization will keep evolving whenever we build new features. So, the way we wanted to provide access for the new features that we build will vary, and the authorization solution should be adaptable to extend for any new use cases. So, the schema definition with tuple based storage. uh, was some limitation for us where we couldn't fit in our use cases in exactly into the schema. So there was a tight coupling with the schema definition. So that is when we started exploring alternatives, and from the learnings that we got from Zanzibar paper and SpiceDB, we had one key learning, which is authorization is a graph problem. So it is connecting relationships between nodes or between entities and using it to derive a particular answer. So with that learning, graph database seemed to be a natural fit for an in-house inbuilt solution, in-house built solution. So the core components to take an authorization decision. So it involves relationships. As we were speaking, it involves hierarchies. We start from a particular group. There can be multiple subgroups that we have to check before allowing the user to perform the action. And there was also transitive access that needs to be covered. So with all these, we chose graph database. And with graph database, how do we solve this? Like, what is the pattern that we are going to use? So here it is like, is there a valid traversal path from the user to the resource or the permission? So we start from the user to whom we want to verify the access, and we traverse through the nodes that he's connected to, and we have to land in either the permission or the resource, or both in cases where both are mandatory, to say yes, you can do this operation, or no, you cannot do this operation. So I think I pretty much already covered where we have built this, but just trying to understand your perspective on where do you think such a complex authorization service should lie. It can, in few smaller companies, it can be inside each microservice, or it can be built as a middleware, or it can be inside product database itself, tied tightly to the product functionalities, or as a centralized service. Any answers? Okay. So yeah, it's a centralized platform service where you have multi-product ecosystem. If it's only a single product, we can go with either of the above options. But when you have multiple products, it will make more sense to keep it at one single centralized place so that everybody else can easily integrate and have the rules at one place. So, what is the need for a platform or a centralized authorization? So, if we have it built in a siloed manner across multiple products or microservices, it involves reinventing the way that every team has to keep building for the same set of rules, the same set of implementations every year. And it will also be hard to audit. A same user using all these products will have different roles at different places, and it will be very difficult to track where the role changes. And also hard to evolve. Whenever a new feature is coming in, it will be difficult for any common functionalities to fit in across all the microservices. So with centralization, there will be a uniformity on how we are dealing with the authorization problem. And there will be clear API definitions that can be used by the microservices to integrate. And there will be a simplified compliance. Audit is at one single place, making it easy for the admin to know who has access to what. And it will involve seamless cross-functional integrations. So this is a high-level architecture overview of how it will look based on how we are building. So let's say there are multiple tenants, and they make multiple authorization queries. So it will go via the API gateway, and it will reach the particular respective product. So in our case, we have fresh service, fresh desk, and multiple products, right? So when a user places a request, it can go to the respective product based on the API path, And the product will then make one single call to the centralized authorization service, asking whether I can allow this user to perform this operation or not. So the entire responsibility of allowing or denying now lies with this one single service. And based on the response, the product can either continue the process or drop the request in the initial stage. So we are using graph database to build this centralized authorization service. So that's the high level overview or the journey that we have gone through before deciding that we are going to proceed with graph database to build this scalable and most performant centralized authorization solution. So I would like to share few learnings that we had over this journey technically and based on the graph DBs that we explored and the graph query languages. So when we decided to use graph database, we had multiple options. So similar to how if we take a relational database, there will be multiple options, MySQL or Postgres. Similarly, in graph, we had Neo4j, uh, Amazon Neptune, and MemGraph. So there are multiple criteria that we looked at to decide which should be the ideal among these three. So the primary goal of these three databases is that, like in terms of Neo4j, it was the native graph DB. When we think about graph database, I think most people will first think about Neo4j. They were the pioneer in graph database world. And then comes Amazon Neptune, which is hosted within AWS ecosystem. It is a fully managed cloud-based graph service. And then comes MemGraph. So MemGraph is like a real-time in-memory graph. So it will be super fast because it tries to solve or store most of the data in memory. But it may not scale for the size of data that we are looking at. And then if we think in the deployment infrastructure perspective, so there as well, we have different options. So either we could self-host these databases and run the queries, or with respect to Neptune, it's an AWS managed service. So we can just provision the database as quickly as possible and start implementing. In MemGraph as well, we have both the options of self-hosting versus cloud providers. Then storage type. How the data is being stored in these three databases. So Neo4j uses a disk-based native storage, and Amazon Neptune uses SSD, and it also has replication where it will replicate the data in multiple instances. So this provides us an advantage of horizontal scalability in data store. Though the underlying data storage disk will be one, but they have multiple query engines running on top of it, which can be scaled horizontally as per our increased throughput. And then comes MemGraph. MemGraph, as I said earlier, it's an in-memory one, so it mostly keeps the data in RAM. And, and once the RAM is full, it will move to the disk. Then the most important factor, I think the subsequent 2 points are the most important ones. One is performance, and the other is cost considerations. So when it comes to performance, all the three being graph database, there will be a similar performance where we can achieve the required milliseconds latency. And in terms of cost, depending on how we host the database, the costs can vary. If we are hosting it in-house, I think we are going to bear the cost based on the instance types or the storage that we are going to use. If we go with the cloud approach, then Neo4j has the hosted version, which is called ARA. So there, I think since they are like an industry uh, standard for graph database, the cost will be pretty high and compared to the other solutions. So Amazon Neptune, it is based on a hourly billing, but for us, since we were already using AWS ecosystem for many other services in Freshworks, I think Amazon Neptune was a easier bet for us for easy integration and in terms of cost considerations as well. So we chose Amazon Neptune for our solution. And considering the operational overhead as well, if it is being hosted in-house, we will have to have a lot of infrastructure expertise in order to handle database hosting. Whereas in case of Amazon Neptune, since it's a managed service, uh, we will not have any overhead and we only have to concentrate on the actual implementation. So with that, I would like to move on to the different graph query languages that's available. So Cypher is the proprietary graph declarative query language that was built by Neo4j, majorly focusing for their own graph database, and it is being shared by MemGraph as well. Whereas OpenCipher is also a declarative query language, which is an open source variation of Cypher. So using OpenCipher gives us the flexibility for choosing any vendor when required. Today, let's say we start with Neptune. Tomorrow, due to some reasons, I just want to switch to MemGraph or Neo4j. Both Cypher and OpenCipher is almost similar, only in one or two features that might vary. So it will be seamless for us to even switch the database when required amidst the available graph database vendors. So to give an example, right, I would like just share a simple example here. So if we want to see the list of groups that a user allies has, so if you see match of user name allies, so this will locate the user node as part of the graph and it will use the member of relationship. So that will be the edge that it will traverse and it will locate the list of group nodes. So in case of group, we have not mentioned any identifiers. So it will locate all the group nodes that are associated with the user node using member of relationship. So that way we will be able to get the list of groups that user allies is member of. So this is a simple example. So this works based on locating the node as the primary step and then traversing it using the paths that we have provided. Whereas we have another variation which is also supported by Neptune, which is Gremlin. So if you see OpenCipher, it's a declarative language. You only say what you need. So on the about query, we only say we need the list of groups in which user allies is member of. Whereas when it comes to Gremlin, it becomes a programmatic ex, um, expression of how to traverse the graph. So we will start with the graph vertex and we will have to say step by step on what is the label that it has to go through, what is the path that it has to go through. So that is the major difference between OpenCipher and Gremlin. So a little bit of deep dive into the overall architecture. So earlier we saw how the centralized authorization service was able to support multiple products. But consider the scalability. So considering a bigger SaaS offering like Freshworks has like around 70k plus customers, the scale is huge and the data that we have to store and the throughput that we have to support will be very high. So in order to support that, having one single data store or one single central authorization layer could make it a bottleneck, or if there is some downtime or some performance degradation happening at that one single layer, it will be a degradation for the overall user experience, which is something none of the SaaS platforms would agree upon. Hence, we wanted to design carefully that our system is isolated for multi-tenancy, so that any impact that happens in one system or one part of the service doesn't impact the overall functionalities. It shouldn't stop the customers from performing what they wanted to do. So, in order to achieve that, we decided to have separate tenants for each product. So, if you see here, so for illustration purpose, we have just taken three products: Fresh Service, Fresh Desk, and Analytics is like a platform where it wants to generate reports on top of both of the above products. So any request that is coming from any of this product will be routed into the centralized authorization cluster. So if you see, the outer box is a platform cluster, and when the request comes in, based on the header, we will identify whether it is coming from a fresh service or fresh disk. And based on that, we will route it to the respective cluster on the respective cell for the corresponding product. So this way, we are isolating the traffic of the entire Freshworks into different products, and hence, like the scale that each product needs will be handled by a separate system. So this is achieved by having multiple Neptune instances. So we will have multiple databases hosted for the respective product. But the core logic of how authorization is solved, that will still be a unified way. So basically, we are just bringing up multiple instances and isolating the traffic, but the core functionality still is the same across both the products. So based on our learnings, I would like to share few things that needs to be taken care of if we are building something with Graph. So the basic of Graph database is how we model it. So we will have to define what are all the nodes that we are going to have and how we are going to relate it between the nodes. And that depends on majorly on the query patterns that you are going to use. So the edge direction, when you're connecting from one node to another, it can be a unidirectional edge. It will be a unidirectional edge. Though most of the databases that we discussed supports bidirectional traversals, it will be performant and efficient if we design the traversal in such a way that it is going from source to target. And we will also have to try and restrict the nodes as early as possible. This is similar to how we do things in MySQL when we evaluate the cardinality, when we perform joins, and try to narrow down the data to as less as possible and then perform the subsequent operations. Similarly, here in Graph as well, when we have conditions to filter out the nodes, we will have to apply it as early as possible so that it doesn't explode and start looking into the entire graph to figure out something that could have been done with just traversing 10 nodes. So there are other options like we do in MySQL. Here also we can run explain to see how it is traversing the graph, and what is the number of nodes it is looking through. So that can be used for optimizations as well. Finally, the way you connect with the graph database. So in MySQL, we'll be using some TCP connections to connect to the data store. So here there is a protocol called Bolt that will be used to connect with the database. And also there are other options like directly doing a HTTP call in order to execute the query. So comparing these two, Bolt using Bolt protocol was highly efficient and it is able to respond very quickly. So that brings us to the last slide. The key takeaways that we had throughout this journey. So we started off from a very base layer where we had to define what a complex authorization solutions requirements will be for such a big scale product. And we start then proceeded with identifying what should be the data store. So there we had multiple options of evaluating whether we go with a buy option based on already established vendors or we build an in-house solution. And then we moved into the in-house solution and learned about graph databases and the intricacies that it had in order to scale for a higher throughput. So if we are planning to build a authorization model, the first thing will be to identify the authorization landscape to start. So to go back to the starting, right, we saw four different authorization models that are available. So among that, based on your use case, you will have to figure out which will be the ideal one for your solution. And choosing that will enable you to drill down to the corresponding database that you have to use. So once we have the first two checked, the next thing will be to optimize for the dominant query patterns. Because if we take, as we discussed, there are multiple authorization query patterns. For our use case, what is the most frequent one that is going to be used? Based on that, the way the database is designed and the way we query can be optimized and tweaked in a higher manner. And then, yeah, that's the next point as well. So, one other important factor is flexibility. So having the flexibility to change the model and adapt for any future use cases will avoid re-architecting the things. Once we have spent so much time in building something that needs to scale, I think it has to also have the ability to be extensible for future use cases. So that is also something I think we should have in mind when choosing the data store or designing for the query patterns. So these are our major learnings, and I hope that will help you as well in building some common solution in your use cases. Thank you so much for the opportunity. Yeah.
Questions? Any questions?
We are open for any questions.
Thanks for the session. Uh, I think Graph DB in authorization is something I'm hearing for the first time. I'm not sure about these many products are already there and about Zanzibar is all informative. Thank you for the session. So my might be like layman terms question is, so if you are using Neptune, which is already in AWS, so what is their that is used? Because their IAM is also a very unique one and is very dynamic one, right? Whenever I write some code to create a custom role, it is created on the fly. So as soon as I create it, within the next API, if I query, it is getting authenticated. So that's the same framework they also use, like GraphDB stuff.
Okay. So you are asking about what AWS uses,
Yeah,
right?
AWS.
Yeah. AWS uses a policy based access control, as far as I know, because it provides us the flexibility to define the roles, right? So, the solution that we spoke is about like we are defining the policies. So it has a slight variation on who defines the policies. And the second part of your question is it gets reflected immediately, right? So that is possible because every evaluation that is being done will be done at the runtime. So soon after you store the policy engine will have the data. And the next time when you ask something, it will be evaluated based on the latest snapshot of the rules that was available. So once you have updated a rule, that will also be taken into consideration for the subsequent execution. And hence it is quickly available. Where we have the problem of immediate availability of an authorization update is that, let's say a role is assigned to 1 lakh users and you're going and adding a new permission into the role. If it is being solved in a native traditional manner, the permission has to propagate for all the 1K users, and only then all the users will get the data. So that is when it becomes an eventual consistent thing. But when there is a runtime evaluation of, you fetch the roles that this user has and then you fetch the permissions that the role has. So if you go in this approach, the data will be immediately available and hence the authorization decisions will be made based on the latest data.
So that is the consideration you did why you chose this part sort of policy, right? That's what you were
Okay. Uh, why we chose this? Actually, policy is also something that we could have done, but policy based access control is more complex thing. And for our use cases, right? So we were tightly relied on the relationships. So there is a subtle difference. So as we were initially explaining, policy based is based on the different conditions that you define. So it can be based on the attributes of a user or a resource, or it can be based on the momentary context. So from which region you are making the request, at what time you are making the request. Are you in the working, if you are making a request in the working time versus you are making a request on an off time or on a weekend. So those kind of dynamic contexts comes into picture for a policy based access control. Whereas our use case was totally on the relationships. We have users, we have multiple entities inside each product. We have workspaces, groups, departments. So all these entities are associated with each other using relationships. So we wanted a data store which is relationship heavy, which is optimal for relationship traversals rather than for conditions like traditional conditions. If not this, so that kind of conditions was not our use case, and hence we did not go with the policy based access control.
Have you considered like building a very complex graph database? The issue is how performant the query is, right?
Correct.
If there is a slight variation in that, then it will keep on browsing in a wrong path and it will take a lot of time to. So where exactly you run, how exactly you optimize, and where is that query running in your structure? I'm not
Okay.
situation wise they will be running.
Yeah.
Where the query is defined and how
So this platform AuthZ is the application that we have built, and this will make a read request to Neptune's read replica. So as you said, it is all about how we define the query. So one mistake in the query traversal path can make it traverse through multiple nodes. So that is why, as part of the key learnings as well, we covered how we have to efficiently write the query, right? Yeah.
For the ease of, sorry, one more thing. You can just draw parallels to your normal RDBMS. Even in RDBMS, you'll have like your source code, which will connect to the database, right? And your source code will have the SQL queries. Here also is the same. So you have your source code. Instead of SQL, it will call a GraphQL query. And then that GraphQL will connect to your database. In this case, this is a graph database, and then return the data. And then your source code will do some operations on top of that, and it will give you the data in the API. So all that remains the same.
Yeah, I see. My opinion, or like general opinion, is RDMS is there for a long time, and that query optimization is gone through a multiple generations.
Right.
This is a new thing. Database, though it's like decade-old technology, adaptation is very rare as
Yeah.
we have seen. So that optimizing something in new tech is a very critical point in this whole spectrum.
Correct.
That's the query. Anyway, thanks.
So Graph DB is there for a very long time. Facebook uses Graph database.
Footprint equivalent to RDBMS, was equal itself less
Yeah.
individual compared to RDBMS. That's the thing. Thank you.
I have a question on top. Is
Yeah.
it all the query, whatever you're defining, is it all predefined? Because you said it is all relation based, right? So is it predefined or the query change?
Yeah, it will be predefined.
So the policy you're talking about is for Amazon, for the IAM.
Yes, for IAM policies that he asked. Yeah. We actually allow our customers to define the roles and privileges only. So we have predefined the queries to work based on the relationships as well as the roles and privileges. So those are the controls that our customers have.
All the SaaS application that you're offering will be role based.
Yeah,
Sorry, not role based.
not role based, relationship based. Yeah. Basically, it will be flexible as a combination of relationship based and role based. Role is an entity that we bring in to avoid permission explosion. Otherwise, we will end up requesting the admin to assign each single permission separately. So, role is just an entity that optimizes or eases the user experience by grouping the list of permissions. Yeah.
So just avoiding the operation.
Yes.
So you have Redis in that package.
Ah.
You had to still more tune it for with the efficient caching.
Yeah, we have done caching because, anyways, the round trip to database is similar to how we consider in relational databases. So, if we wanted it to be highly efficient and perform within milliseconds latency, right? So, we will be caching the response in Redis and we will use it. Whenever the data changes, we will invalidate and we will again make a query to the database.
Passive setup, like database that will be active and
Redis will be
first session to second cell. That is
okay. So this is a writer instance and this is a reader instance. This is the architecture of Neptune. As I was telling, Neptune has one single storage layer and it has multiple query engines built on top of it. So we can have any number of reader instances because that does the actual query optimization and the execution. Only the data is being at the lower layer. Hence, for any read-based flows, we will be using the reader instance. And write has to be consistent, right? And hence, the writer instance cannot be horizontally scaled. So that will be one single writer instance using which it will write into the data stream. And these two boxes are just the multiple tenants that we have within our ecosystem. So for every product, we are having a separate cell.
The top
So
one
that's
is for fresh service. This one is for fresh desk.
and we differentiate where the request has to go using Istio proxy. We use the headers to identify. So this is to avoid net throughput overhead on one single system since we are dealing with a higher throughput. Yes. So basically, the solution that runs on this platform also is going to be the same in both the cases. It is only different instances to split the traffic and the complexity.
how it gets scaled in terms of multiple nodes.
Graph scaling, you're asking. Okay. So that's an interesting question I was expecting. So in graph database, if okay, I had a so I missed on this part example graph I had. So this is how we have define the entities, like we have account, departments, and roles and permissions. So when we speak about scaling, right? So there is a possible. It is about the number of nodes that you traverse through, and that depends on where you start and how you filter out the use cases. So when it comes to authorization queries, we mostly start with the user node because we know for whom we are querying. So from the user node, it depends on the number of groups that is associated to, the number of departments. Based on that, the traversal will scale. So if we compare it with relational database, if we are doing a join, then from for one single user in table B, if there are 10 rows, then it is a cardinality of 1 is to 10, right? Similarly, it depends on the number of edges that goes out from a single node. So if that is very high, then we will apply additional filters on the resultant nodes. So there are like 100 nodes, if, let's say if it is there, but all those 100 nodes will not be of the same type. 10 will be of groups, 10 will be of departments. So we have additional conditions that we keep adding to the resultant nodes. So that is how we narrow down. And the scalability depends solely on the number of edges that you traverse.
Same thing used for service account support, like non-people service application to application accesses.
Right now, we have not only for user.
So those users, whatever they're talking about is native users, native to that application.
Yeah, customers of these products, Fresh Desk and Fresh Service.
Overall, when you say that this kind of critical, crucial application is stamped and sent to prod now. So what is the performance benchmark you did basically for this database? Let's say how many number of nodes with X number of relationship complications that you thought about.
Okay.
We had that slide. We removed it.
So
We have-
I don't have the exact count of the nodes and relationships, but we have the data on like the number of accounts we used, right? So we populated up to like 5K accounts data, and like each account having up to 1K to 3K users in it with different groups and departments. And we performed a benchmarking of up to 120K RPS, requests per second. 120 requests, sorry, it's not 120K, it's 120 requests per second, which will be around 6,000 RPM. So with that, we were able to see for the native check permission, we have like less than 10 to 15 milliseconds. And the complex query pattern that I was speaking about, fetching all the permissions across all the resources, it will be under 50 milliseconds, 50. So that was the benchmark that we were targeting, and we were able to achieve that. 50 milliseconds.
Under 50 milliseconds.
5GB you showed 15 milliseconds. That is a difference.
Permission. So two different query patterns are there. Check permission, both with 5GB as well as Neptune, it's 10 to 15 milliseconds only. But the other query pattern, because check permission, you have both the source and the target. You start from the user, you know what is the resource that you want. For the other use case, I'll have to collect the full branches out. So there, SpiceDB, it took seconds for us, but here we were able to achieve within 50 milliseconds. I think we can wait for 15 minutes for the questions. Thank you so much for all the questions.
Thank you.